Hey guys, and welcome to the video of me working the 6-4 practice problems for you. Now this is a section based on some of the stuff that we were talking about before the break, but it's been a minute maybe. I don't know, maybe you don't remember how to do this stuff. In which case, I'll do these problems and hopefully that'll jog your memory and you'll get a better understanding. So we want to factor completely in this section. 6.4 specifically is for three different types of factoring, and that is difference of squares, and the perfect square trinomial, and the sum and difference of cubes. And those are the three types. So we're starting off with 49x squared minus 9. And if we want to know what to do with this problem, the clue is perfect squares. So if you remember all of these squares, that's not one of them, hold on. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and then 121, and 144, and so on and so on. These are the numbers you're looking for to know whether or not this is the difference of squares. And look, 49 and 9 are both on this list. So, because of that, I can split this up into two parentheses, where I break down 49x squared into its two parts, 7x times 7x, right? So these two guys multiplied together give me this, and it's perfect squares. 9 splits up into 3 and 3. 3 times 3 is 9, right? So it's the exact same terms as each other, only one of them has a plus and the other one has a minus. And that's done. So these are really quick as long as you can recognize the perfect square numbers and be able to break them down or take the square root correctly. So let's try it again. 16k squared minus 81m squared. So the letters also have to be squares, and so they have to be even powers. But 16 and 81 need to be on this list. Oh, look, there's 16, there's 81. Yay. So let's break them down. 16 is 4, don't forget your k, and 4k. 81 is 9, don't forget your m, and 9m. And then one's plus and one's minus. All done. So that's difference of squares. Here's another one, 4 minus w squared. And the reason why this is on here is because I've seen this mistake being made before. So a lot of times we're very, very used to the letter coming before the number when we write our polynomials. But this case, since 4 is first, the breakdowns 2 times 2 are first. That makes a difference. W comes down in w squared becomes w and w. And it'll be plus and minus. And you can be like, well, can't I just write w plus 2 and w minus 2? No, you'd be wrong. Keep the order. That's the point. Number 4, we're talking about 25 c to the 10th minus 1. So here's a good indication of what happens when the letter is not a square, but it's even. Well, we have to think about what two powers added to give me 10. So 25 breaks down into 5 times 5, but c to the 10th breaks down into c to the 5th and c to the 5th. So when you multiply these two together, you get 5 plus 5. That's what's happening. So when we break down numbers, we break them down into square root. But when we break down exponents, we break them down by dividing by 2. 10 divided by 2 is 5. 10 divided by 2 is 5. 1 breaks down into 1 and 1, and then we put plus, minus, and we're all done. Okie dokie. That's 1 through 4. Now, number 5 through, just 5. 5 is one of those problems that looks like something, but it's actually two things. So this looks like the difference of two squares, and it is. This is 9, and this is 9, and this is square. They're all squares, and this is a minus sign in between. Yay. So I could go 3x minus 3, 3x plus 3, right? Technically, yes, you could. But what I want to do is GCF first. always, GCF first. So they both have a 9 in common. This guy and this guy have a 9. And when I divide a 9, I get x squared minus 1. Now this is a difference of two squares as well, but the 9 is pulled out. So when I break down x squared minus 1 into two things, I'm not including the 9. So x squared becomes x and x, 1 becomes 1 and 1, and then I have plus minus. And that's the correct answer. Now if you have 3x plus 3 and 3x minus 3, that's not wrong as how you factored it, but it isn't a fully factored function. Like it's not an answer that's fully factored. And the reason why is because there's a GCF in each one of them. Okay. Perfect square trinomials look like normal trinomials. And you could factor this using one of your old trinomial forms. So like this, you could do the x method, put an 8 up here, 16 down here, and all that business. But what we could do is we could look at the first and last term and see that those numbers are on this list. They're squares. And then I say, okay, well, what happens if I break them down? X squared would become x, 16 would become 8. I'm sorry, 4. 4 times 4 is 16, not 8 times 8. Getting confused. And then I can say, wait, if I put these two together, multiplied them together, that would be half the middle. So the question for perfect square trinomials is the product, when you multiply, of the square roots half the middle term. So when I take the square root of the ends, I get x and 4. And when I put them together by multiplying, I get 4x. Is that half of 8x? Sure is. Then if it is, you bring down the first plus or minus, no matter what it is, that comes down. And then we wrap it up with a parentheses, and we put a square on it, and we're all done. So we don't have to do it with the old, like, x method or anything like that. We could do it this way, which is nice. It's actually pretty quick. So this one, we have x squared, xy, and y squared, and that still fits the form. It's okay to do this factoring like we normally do, like if the y's weren't there. So you do the thing, I look at it, and I go, wait, that's a square, and that's a square again. So let's break them down, square root them, x. Square root this guy, we get 4y. I'm doing it right now. And then I go, okay, what happens if I multiply them together? I get 4xy, right? That's half the middle, isn't it? So I can bring down that first symbol, wrap it up, put a square on it. We're all done. Nice, huh? All right, going down to 8. 8's the sum or difference of cubes. Now here, we want to look at the different cube numbers. So 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125, and so on and so on. It starts getting big after that. So these are the numbers I'm looking for when I want them to be cubes. And this first one is a cube number. I just didn't get to it when I was writing. But I believe it's 9 times 9 times 9. I'd have to check. Hold on. Bring up my calculator. 7, well, I want to do the cube root of 729. So 729 cube root. Yep, 9. So this is 9 times 9 times 9. And so this is a cube. And this is a cube. So the way this works is a weird thing. So there's 2 terms in the first parentheses, and there's 3 terms in the second parentheses. Always with cubes. This is the setup. Now the first 2 are found by just taking the cube root. So like this guy is 9, and this guy would become p. Cube root of 1 is 1. Okay? So cube root, let's find the first 2. For these 3, I got to look at these 2. So this guy is whatever he is times himself. So let's like say A and B. This would be AA, this would be AB, and this would be BB. Does that make sense? So we're going to multiply this guy by himself and get 81p squared. That's 9 times 9 and p times p. And then I'm going to multiply 9p times 1 to get AB. And I'll multiply 1 times 1 to get BB. BB. Right. Now we got to use SOAP. SOAP means same, opposite, and then always positive. Whatever, you get it. Same, opposite, always positive. That's the idea behind finding the signs of a cube's factoring. So this is the same. And then from here to here is opposite. And this last one is always positive. That's how we do that. Let's try number 9. All right, number 9 says t to the third. That's a good indication. This is a cubic thing. And then 512. Okay, now I got to figure out if 512 is a cube. Go to my calculator. I write in 512 and then hit the cube root button and I get 8. Yes, it is. So this is a cube and this is a cube. So when I do the setup, 1, 2, and then 1, 2, 3. That's what I got. And I take the cube root, I get t. I take the cube root and I get 8. And then I go this guy times himself, this guy times this guy, and then this guy times himself. Right? AA, AB, BB. And then I use SOAP. So same, opposite, always positive. Okie doke. All right. And then there's one more. So I'll try to sit it right here in this little space because I don't want to start a brand new paper for one more question. Sorry. So here we got a cubed b cubed plus 729. And again, I know 729 is a cube because of a previous problem. And these are both cubes, so this works. 1, 2, 1, 2, 3. And then I break them down. A cubed, b cubed just becomes AB, right? And then 729 is 9. Now to figure this one out, I go this guy times himself, so a squared, b squared. This guy times this, so it's 9ab. And then this guy times himself, which is 81. Now I use SOAP, same, opposite, always positive, and we have our answer. A couple of things to note. This trinomial never factors. Never factors. Not traditionally. And the cube thing works whether you start with a plus or a minus. It doesn't matter. But the square thing has to have a minus for it to work. If it has a plus, you're going to put prime, or you'll do just the GCF and be done. So when you're looking at this difference of squares, it's got to have a minus. When you're looking at cubes, it can be both plus or minus. It doesn't matter. They're just different techniques. All right.